2,955?
Yeah.
And how many million are we going to do that by?
5.
5 million. All right. Hey folks, welcome, and welcome out there to TNLearn Mathline this afternoon. I'm your host, Ernie Roberts, for this afternoon session, and it is another Specialized Segments Day. You say, well, what does that mean? That means you get to sit back, relax, get some pencil, get some paper, maybe even a calculator, probably not needing that today. Let's get ready to do some math, working problems without call-ins. No call-ins today, but you can still send us problems via email, Facebook, however methods you want to get to me, all right? You can still send those in. We'll address them in our next live show. Again, no number to call today. Just sit back, relax, get the pencil and paper. And guys, let's see what we're going to relax and do, all right? What do we got going here? Got presenting the great isosceles right triangle. Wow, isosceles right triangle. That's a mouthful. It's a mouthful, but it's a big deal. It really is. So what are we talking about here? First of all, the word isosceles means we have at least two congruent sides. And in an isosceles right triangle, we can only have two sides congruent. All right, can't get all three of them. All right, but by definition, isosceles means at least two. And then we have a right angle involved there, and that's going to have to connect our two legs. So that gives me a little hint that if it's isosceles right, it means the two legs probably have to be congruent because the hypotenuse is always the longest side. So there's the setup. Let's see what we're going to be looking at. All right, let's take a look at some problems here. First problem, right off the bat, we're going to go through it. We're going to work it. We're going to find the length of the other sides of, oh, what did I use? I didn't use isosceles right. I said 45, 45, 90. You say, Ernie, where did that come from? Well, the 90 obviously comes from a right triangle, all right? The 45, those are angles, all right? 45, 45, 90, those are the angle measures. Right here we go. So we'll put 45, that's degrees, 45 degrees, and down here we got our 90. So first of all, that's what you got looking at, all right? Now, take a look at it because, well, it's going to be there for a minute or two, right? We are worrying about finding a leg and a hypotenuse because we've got one leg over here. We'll call it 3. What does that mean by being isosceles or by being 45, 45, 90? That means these sides are congruent. Those legs, by the way, not just a hypotenuse, ain't going to get into this game. It's just all about the legs to be congruent. So we'll put our 3 right there. And then we've got some question mark. We don't know what the hypotenuse is. And you say, why'd you put a 3 there? Isosceles. Same length, both sides of the legs. All right. So that was easy. Yeah, you said, well, that was easy. So how do we get to the hypotenuse? Well, already a lot of you are out there thinking, I bet you're going to do that a squared, b squared, c squared thing, which is all about what? The Pythagorean theorem. Why not? Let's go for it, all right? So we're going to take the 3 here. We're going to go back. I'm going to go back to you here, all right? I always like to put down the formula. And yes, right triangles do come back to Pythagorean. By the way, this is just a nice, what we call special triangle version of a right triangle because it is isosceles right. And hey, we're presenting them and they're great, right? So here we go. We're going to put our numbers in here. How about it? Put a 3 in for A. Also, folks, B is the same. So we'll put a 3 right in there also. And we'll come over here and we'll say equals to c squared. Little algebra going on here, little substitution. And when we square the 3, we do come up with 9. We square it again, we're still going to get 9. It hadn't changed in the last 2 seconds. Don't put a 2 down there. I was about to do that because I was thinking. Don't think. Let's just do the problem, right? And we've got c squared, and we're ready to pull this together. I've got 9 plus 9. Don't put times there. That's a plus, all right? Very important. We've got 18 equaling to our value of c squared. We say, well, Ernie, it's not a perfect square. Well, you know, you're right, folks. I'm right on that too. So what are we going to do? We're going to pull c squared over here, and we're going to say it equals 18. We need to get back to square root, the square root of c squared. That will get us to the answer c, all right? If we square root the left, we must square root the right, okay? So let's go to the other side. We're going to have to square root there also. That's where we have to think a little bit. You're saying, well, do you just go to the calculator? We could. If it just asked for you to give the number into the nearest hundredth or in the nearest tenth, we could do that. But I want to go for what we call simplest radical form here, all right? Because we are doing these kind of problems, and the radical is important, so we're going to worry about reducing the radical or simplifying, all right? Although, truthfully, what you'd like to do is probably say, hey, how long is that? And we'll check it in just a minute and find out. 18. We want to break it down. We want to factor it down, but we want one of the factors to be a perfect square. So we start thinking, how do we break down 18? Well, it's pretty easy. Do 3 and 6. But 3 and 6 doesn't help us because 3 is not a perfect square, nor is 6. Not going to help. Let's try 1 and 18. Well, 1 and 18, 1's a perfect square, but the root of 1, the square root of 1 doesn't help us, all right? In fact, the root of 1 is just 1, and you're just going to be right back where you started. So what we got to do is there's one other option. How about 9 and 2? Let's put 9 times 2 right in there. Why did I do that? Because that's a perfect square. 2 is not. So here's what's going to happen. Watch closely, my friends. Watch closely. The square root of 9 is a 3. It comes to the outside, all right? The root of 2, well, it doesn't do anything except stay irrational, very irrational, and there you have it, all right? So there's your final draw there. You say, that's all there's to it? That's all there is to it. Once you get here, find yourself a perfect square that'll divide into the number and then take its square root. That is doing it the rational way, all right? Well, actually leaving the irrational out, but you're looking for some rational parts, all right? So that's using the radical approach, all right? Radical, rational, irrational, 3 great big words that have R's involved in them somewhere. Let's take a look at what this actually is in a value, all right? Let's go to the calculator. First of all, we're going to pick up 3 times the square root of 2, because I like for my folks to be understanding that these things that we do, what looks like little tricks, actually give us the same values. They're just simplified versions, all right? We've got, if you'll notice there, 3 times the square root of 2. Let's hit an enter. And it says, wow, that's about 4 and a little chump change there, all right? 4 2400ths if you want to take it to the nearest hundredth, or 4 and 2/10 if you want to take it to the nearest. Usually we round off because this thing rambles on. Let's bring it over there, that cursor. Come on, little cursor, you can do this. Maybe you can't. Let's see if I can get you. There we go. It rambles on and on and on and on and on, all right? So we round off to one of those places, maybe tenths there or hundredths. Very seldom do we ever go to thousandths and other things because it gets kind of old and boring. Now, not really, it's just that you get a pretty good representation by the time you're at hundredths place or tenths place in these. Now, let's go back and check one other thing. The reason I want us to look at this is this actually the same thing as the square root of 18? Some of you are already going like, well, I bet it is. He wouldn't tell us otherwise, would he? Well, let's see. We'd put 18 in there in the little box. We'll press enter. And my goodness, it's the exact same thing to the exact same decimal place as everything. So that tells me, folks, that 3 square roots of 2 is the same value as the square root of 18. This is what we call simplified radical form, all right? This is nice. This is the decimal approximation, all right? So again, it's still an approximation, even if I use all, goodness, how many places? There looks like 9 places there in the decimal, all right? Even if we use all, maybe even more. No, it's 9. 9 places in the decimal, then count the 4 would be the 10th, but that 4 is not in the decimal place. So we look at these great things, and again, I digress a little bit, but I want you to realize, yes, those do relate to being the same thing. So we're going to play with simple radical form today, all right? That's going to be our story rather than trying to make these things nice decimal approximations. You can always go to your calculator and do that. All right, let's do that. And if your problems are asking you for the nearest 2 decimal places or nearest hundredth or nearest tenth, so be it. Do what they ask you to do. All right, go there. Today, like I said, we're going to hang out with radical form. Let's take a look at our next problem. All right, another 45, 45, 90, which means, yes, it's one of those great isosceles right. There's the right angle waiting for us. That's the 90. Because remember, these are all like little degrees. You can put little degree symbols if that helps you remember. But we usually just say 45, 45, 90 degree triangle. And we're going to give you a leg. Again, well, that's a leg. Remember, the legs make the right angle happen. The hypotenuse is sitting out over here by itself. We don't have a clue what it is yet. Well, we probably do. Some of you probably already figured it out because I talk a lot, don't I? And we have an isosceles situation. You say, how do you know, Ernie, that we got an isosceles situation? We understand how we know we have a right triangle. Well, once these 2 angles up here, which are both 45 degrees, once they are congruent, and they certainly are, that will force these legs, which are the sides opposite those angles, to also be congruent. So the 5 over here becomes the 5 right here, and we're going to attack it with good old Pythagorean theorem again. Now, some of you out there who are already taking special triangles in geometry say, Ernie, isn't there a shortcut? There is. We'll see if we can get around to that, see what happens in just a minute on that, all right? Now, looking at this problem, though, let's go ahead and run it through with Pythagorean theorem. So we're going to start with a squared plus b squared equaling our lovely c squared there, all right? You got it? Clap, clap, clap. Yeah, you do. Now, put in 5 and square it. Put another 5 in and square it. I see c squared, not going anywhere yet, all right? So we're going to add 25, 25 together. It's going to give us a big old whopping, well, let's put it 25. We need to show that, don't we? Some of you are going, where'd you get the 25? That's what 5 times 5 is, right? Don't put 5 times 2. It won't be right, okay? 5 times 5, and that's 25. 5 times 5 again, another 25. Add them together, I see 50. You see 50? We all see 50, right? Okay, there it is. C squared equaling 50. It is time to square root both sides. This sounds like the same story we did, wasn't it? Well, it is. And notice, we're starting to see a pattern. A pattern might be important to notice here in a little bit. Seems to me like we're going to take the square root of c squared. Well, how about it? That gives us c. That's what we're after. All right, because we weren't worrying about what c squared is. We want to know what the actual length, that hypotenuse is. That's where we're going. That's where we're going. So we think 50. Remember what we did a minute ago? Oh, some of you just tuned in, right? We're going to look for a simple radical form of this. This is nice, the root of 50. You go hit it, square root of 50. You go punch it on the calculator, and it's going to give you something, probably about 7 point something. But let's go for radical form. Look for a factor. Look for a factor of 50 that is a perfect square. Now, 25 looks good to me, all right? Because 25 is a perfect square. 25 times 2. Folks, when you see numbers like 50, 25, 75, 125, think about your money. Those are quarters, all right? That's like 2 quarters. So it's easy to remember. You're going to say 25 times 2, all right? There you go. And by the way, square root of 25, we know that. That's 5. We do know that, right? Everybody got it? All right, we got 5. What's left behind is that square root of 2. And we got a little value of c right there. So here we go. So now, this is one thing I'm noticing. It looks like if a equals 5, we had c equaling 5 square roots of 2. And a minute ago, we had a equaling 3. And of course, the other leg, b, is just always the same as a because it's isosceles, right? So what about it? C was equal, as I recall, and hope you all recall, was 3 roots of 2. Now, there's something going on here. Notice we just slip and slide from 5 to 5 roots of 2, or 5 square roots of 2. These are our square roots, not cubed or fourth roots. We're just at square root land here. And 3 goes to 3 times the square root of 2. I bet if I put a 6 in for a, I'd have 6 times the square root of 2. Sounds like a formula in the making. I tell you what, we may have a chance to look at the end of the show, but if not, it'll be in our next Specialized Segments program, all right? We're going to look for a formula and a shortcut and ask ourselves, does this work every time? I bet a lot of you are going like, I bet it does. But we have to prove it for everything. So we're going to, instead of putting numbers in there, we want to play with A's and C's. We'll try that next time, all right? Just hang on. That'll give you something to look forward to. Today, let's just crank it out using Pythagorean, all right? Let's just keep on cranking with Pythagorean. Like I said, another whole show looking for shortcuts. Just want to let you know that we are going to get there, all right? Now, let's pick up our next one here. Another 45, 45, 90 triangle coming our way. This time, this time I make you miserable. I said a leg is going to measure 3 times the square root of 2. It's still a 45, 45, 90, which means isosceles right. So here we go. Pick it up. Right there's the right angle. Ooh, a lot of rights in that sentence, wasn't there? And here we have our 45 and our 45 because there's nowhere other place to put them. They're the 2 angles, all right? Which picks up a pair of congruent legs because remember, if the angles in a triangle are congruent, if 2 of them are, then those sides opposite are going to be congruent, all right? And that's what the isosceles triangle works there. You can go from sides to angles or angles to sides. There's some nice theorems that allow you to do that, all right? So here we are, back again with, this time, 3 times the square root of 2 for the leg. Now, some of you just saw the last problem. You're going like, okay, Roberts, how are you going to get out of this one? Like I said, we're going to go Pythagorean theorem on this. We'll play those shortcuts on down the road on our next session. But we've got 3 times the square root of 2. Pop it in there, square it. And we're going to do the same thing here. We're going to square again. And that's going to give us, of course, our lovely c squared out there. Everybody with me? Y'all good? Wow. Now the next question is, what do we do? How do we take 3 times the square root of 2 and square it? I'll tell you what we're going to do. We're going to make this easy. Everything inside this radical needs to be squared. So when I do that, I say 3 times 3, I get, you got it? Kick, 9. Of course, it's easy, isn't it? But what about the square root of 2 times the square root of 2? In other words, we're going to take 3 times 3, 3 times itself, and we're going to take the square root of 2 times the square root of 2. Well, you're thinking, I hope you're thinking, you get a square root of 4. Oh, 4? Oh, that's a perfect square. I know the square root of 4. That one's easy. I don't have to go to a calculator and see it ramble forever. It's 2. So here we have it. Let's look at this. This is going to be 9 times 2. And that, folks, takes care of the squaring. All right, so we've got a 9 times 2. We'll deal with that. Over here, I've got 3 squared. Same story, isn't it? And again, take square root of 2 times square root of 2. That's going to give me 2 because I did the mental math on the 4, right? So we put times 2. Notice the radical is gone. It's gone. That's the beauty of this. We can't get rid of the radical. We got a few problems there. And then we got c squared to hang out. Notice the squared is gone. The radical's gone. Life is good. Life is good. All right. So I've got 18 plus 18 equaling our c squared, our hypotenuse squared there. And kicking that together, oh, I got 36. I like this one. You know, I really like this one. You know, you say, why do you like that, Ernie? Because it's a perfect square, folks. Yes, it's a perfect square. And the square root both sides, and you know what? C equals to 6. Now, I'm going to tell you something. This little step you guys can do in your head. You can square that 3 and say, oh, that's 9. Hold it for a second. You got at least a second or two of an attention span. Yeah, everybody does. Then take that square root of 2 times the square root of 2. It's just going to give you 2. Get that in your head. If it was the square root of 3 times the square root of 3, it would be 3. But we're dealing with 2's here, all right? And there's your story. 6. Ooh, that was nice. No radical, no root, no square root anywhere in that last answer. 6 of the hypotenuse. By the way, the other leg was 3 square roots of 2. And by the way, these would be, of course, centimeters if you want to get the measurement on there. We always like to do that. So all these are centimeters, and these are centimeters. Big thing I'm worrying about is making sure we can get through the mathematics to get to those units, and then you can just apply the units that you're given, which are right there, into your triangle. There you go, all right? So there's a third. There's a third problem. Now, let's try one more like it. You know what? There's always seeming to be a pattern popping up on some of these because they're called special triangles for a reason. That's because there will be a pattern. There will be a formula, but not at the end of this lesson. It'll be at the next time we pick up. Let's take a look at our next problem here. Let's take a look at this one. It says find the length of the other sides. Again, 45, 45, 90. That's all we're playing with today. We are having a right triangle going with the 90. Once again, we got the 45s going. And some of you are saying, Ernie, that turned a different direction, didn't it? Yeah, it's kind of looks like it's facing off to the left where the others were facing off to the right. That's okay. It's still a right triangle. These are still the legs. They are still congruent. So we know this is 2 square roots of 2, and it's feet this time, all right? This is also going to be 2 square roots of 2. Guess what? That's because they're 45, 45, 90s. That is easy. That's your easy part right there. The big question is, what's going to happen with C? And I'm sure some of you are already going like, I don't know. And some of you are going like, I do know. So let's find out and let everybody in on the secret, all right? We're going to take that Pythagorean theorem once again. We're going to take 2 times the square root of 2, and we're going to square that value. Whew, look at all those 2's. We'll keep up with them. And do the same thing again. More 2's. Goodness sakes, 2's, 2's, 2's. And we'll put a C there for good measure because that's Pythagorean. A squared plus B squared equals C squared. That's where they came from. Now, remember that little shortcut I just told you in the problem code? Some of you are just tuning in. Sorry, you'll just have to run along with me, okay? But we've got here, we've got it going. We have 2 squared, which is 2. And we already know that square root of 2 times the square root of 2 gives us another 2. So what did I say? 2 times 2 is how much? Did I say 2 or 4? I don't remember. But it's 4, all right? 2 squared is 4. And then this is going to give us 2. That gives us 4 times 2 in your head, 8. Sometimes my brain gets faster. Sometimes it's really slower than my mouth, okay? So just be patient with me here. 2 squared, again, we're going to play the same game. We're going to square that 2, and then we're going to take the square root of 2 and square it also because all of that is inside nice multiplication parentheses. So it says square the 2, square the square the square root of 2. Boy, that's like crazy, all right? Guess what? You're going to get 8 again. How do we do that? 2 squared is 4. The square root of 2 times the square root of 2 is 2. So 4 times 2, hey, I've got another 8 out of that. Don't let these numbers get you scared. Don't let it get you nervous, all right? Equals, got it, c squared. How about it? 8 plus 8, I like that. 16, you get a c squared. Root time, all right? And here we go. Square root of 16 is 4. Square root of c squared is, c. There it is. Patterns. Let's see what we got. I'm seeing a was equal to 2 times the square root of 2 here, and we got a c value, hypotenuse, of 4. And a minute ago, we had the a at 3 times the square root of 2, and the c ended up being 6. Patterns? I think there are. We'll find out next week, all right? Next specialized segment of time. Let's take a look at a sample when we know the hypotenuse, all right? We have to look back for the legs. Again, 45, 45, 90, isosceles right. Big stuff here today. This time I'm giving you C. We hadn't had C yet today, all right? Last 2 problems here, we're going to pull it in, all right? We got a 12 right there. On the left side, I have an A. Oh, by the way, there's the right angle because there's the hypotenuse. There's our 45 up there for those of you, again, just joining us here. There we go, 45 and 45. It makes a nice isosceles right triangle. There's an A. We're just going to call it A. Not going to put a B there because it's the same value. Same value. Remember, legs are congruent when these 2 angles are both 45. When they're congruent, we're going to get those congruent sides here. Doesn't work if it's scalene or these angles are anything different. These are going to be different that way. But when they're 45 and 45, that's the only way these work the same. Let's go a squared. And this is what was going to happen here. A squared plus a squared equals, how about it, 12 squared. Wow. All right. Big numbers? You learned your 12 times 12s when you're in 4th grade, right? Some of you go, I forgot them. Calculator might help you, but 12 times 12 is 144. That's the only thing you really got to know here. It's the only thing you got to worry about. I have an a squared plus an a squared. Now, contrary to popular belief, and this is a total myth I'm about to tell you, a squared plus a squared equals a to the 4th? Not. That is a myth, okay? That's contrary to popular belief. If there had been a times between these, it would be a to the 4th, all right? But plus, no. What we're doing, we're taking 1 and adding another one, and guess what we have? 2a squared. Exactly, 2a squared. One of the most fundamental, 1 plus 1 equals 2. When did you ever think you would do that again in high-level math? Here it is, all right? And we've got the 144. Divide that 2 through there, kick it out. We have a squared equaling, something we don't like to look at, 72. Why do we not like to look at that? It's not a perfect square. But let's see if we can find a possible perfect square as a factor. Actually, there are quite a few with 72. Let's go high. Let's go the high root. And I can divide 2 into that evenly, which gives me, what, 36? You know what the high root is going to be? We're going to take a square root of both sides. Let's see if I can make a square root look good. And underneath that, we're going to break that down. I just said 36 times 2. 36 is a perfect square. 2 is obviously not. All right? And what that's going to give me is 6 times the square root of 2. Remember, the square root of 36 is 6. Pull it out. Leave the old root of 2 behind. So that's what this a equals. It's also what this a equals. How about that? All right? Not bad. Not bad. And when we look at this, all right, again, there's that pattern. I'm asking, did you notice something here? A equals 6 times the square root of 2. C equaled 12. Well, we had 2 others that are sort of like that. We had a root of 2 here, but not a root of 2 there. Oh, so square roots are getting in the way, some, aren't they? Things to think about. I'll go ahead and give you a hint. Let's go look real quick at that problem one more time, all right? Formula, I'm going to tell you. To get from A to C, you've got to take a times the square root of 2. Now, I'm giving you the formula. We're going to prove it. okay? And it's going to take about 3 minutes to prove on the next show, all right, on our next specialized segment. So you be sure to tune back in then, because we want to show that this works not just for 6 and 3s and 2s, it works for all of those numbers, okay? The relationship between A and C is dealing with the square root of 2. It's a very critical moment, all right? We'll look at it, like I said, look at their next specialized segments. Thank you folks for tuning in today with us, all right? It has been a specialized segments, which means we basically look at a topic and explore it and sometimes take it in pretty much in depth. This time I try to keep moving you along, but remember a 45, 45, 90 and an isosceles right triangle are one and the same, And the key factor is going to be a lot of square roots of 2 involved, And that will lead us to the formula, like we said, C equals A times the square root of 2. We're going to explore that. And you know what? We're going to make some shortcuts, because this took a long time to get through 5 problems today. We're going to take it and make it easier next time. Hey, thanks for tuning in. We're live again next week, but thanks for today, and we will see you next time.